Hello. Can you wait a minute? Can you hear me? Wait, I might be muted. Wait. Hello. Can you am I good afternoon? Am I muted? Can you someone say good afternoon? Can you hear me? You can't hear me, can
We can hear you.
you can. Oh, thank you. And who was that? Was that okay, thank you. Thank you. Okay, awesome. So hello, Katie. Hello, Josephine. Hello, Claudia. Hello, Maria. Hello. And we're okay. And afternoon, Eric. Good afternoon. Oh, and yes, you can hear me. Okay, sorry. See, I could. Okay, thank you. Good afternoon, Alexis. Good afternoon, Jada. Good afternoon, Victoria. Good afternoon, Maria. Good afternoon, Paulina. Good afternoon, Claudia. Good afternoon, Stephanie. Okay, and Shy and Emily and Emily. Well, oh, okay. I won't press my luck. That was exactly okay. So I want to and good afternoon, Shy. And Logan, I'm sorry. Hello, Logan. Good afternoon, Logan. Okay. I want to do our last bit of Newton's. Well, I want to do a little bit more about Newton's laws and forces right now. Two quick questions. One, in the most recent lab that you, and good afternoon, Stephanie. Sorry, and good afternoon, Claudia. Or I'm reading this out of order. Okay. In the hello, Alan. All right, excellent. Hello. I have two quick questions. The lab that you did, the slow down lab 5, slow down. You have at this point turned in formal reports. Is that no? You have not. Oh, okay. Thank you, Katie. Okay, that's very good. I mean, not until the end of December. Okay. Then I think this will definitely not be wasted time for you. What we're about. Then my other question is, wait, you have Professor Walters in this section, right? Yes. Okay. So did you guys do a board meeting? Did you ever do a board meeting involving forces and Newton's laws and so forth, but that had, or have you ever seen a problem where there was an inclined plane accelerating forward horizontally on a like there was a block on an inclined plane, but the whole inclined plane was accelerating forward? Is that familiar at all? Or is that like out of that's a yes, Claudia? Or wait, no, but Katie's sort of going, wait, okay.
Are you asking if the block on the inclined plane is moving or just the inclined plane itself is moving?
Okay. I'm asking, right, good question. Like I know that in your lab 5, which is mostly what I'm going to talk about today, I know that in that lab you have a plane that's stationary and a block or something is going down it. But then there's this other sort of famous problem that some sections seem to have seen and some sections haven't, and it's okay either way. But there's a famous problem, not a lab. It's a problem, but that some people saw in lab where you have a plane, like a slide, but the whole slide is actually moving horizontally. And by moving horizontally, it keeps something stuck on it. Is that, and if you haven't, it's very, very likely you have not seen it at all, but I just, one section happened to have seen it. So but if that doesn't ring a bell, that it doesn't.
Yeah, we might not have seen that because the last lab class that we had was going over lab 5.
Okay.
And like getting the dates for our formal report and our lab reports. So we didn't do the board meeting that I think your previous class had done.
Okay.
Our class is a little crazy because between Walters missing a class and then also just like I think we had a day off or something, and then like it was done in a different order than I think we were supposed to. So this entire lab is like
Okay. No, it totally makes sense. Both of you, all three of you, Claudia, Katie, and Maria, totally clarifying and totally fine. And I'm looking in the chat. Okay. And people in the chat are confirming what you're saying. Okay. That's totally fine. I just want to make sure. I just don't want to talk about things that's totally okay. And the formal report also in the class. Also in class. Right. Okay. Okay. That's totally fine. Okay. So then what I do want to do today, I want to talk more about inclined planes today. Some of the things I want to do today are definitively, absolutely things that I'm going to say that I know you haven't seen in lab, and especially now, given what you told me, and I'll let you know when we get to those. But especially since you have not turned in your formal lab report, I first want to help with that. I mean, I started helping hopefully with that like last Wednesday. I have a little bit more that I want to say that I think might be directly helpful with that. But before I even do that, since I already talked a bit last Wednesday, and since you're all being like giving me this helpful information, I want to just say, like, literally, is there anybody that wants to ask any kind of question? I'm here to answer questions first. Any question about anything that is unclear in that lab, and specifically anything that is challenging you in trying to write a report, I would like to help and try to, because it's a pretty important, there's a lot of important ideas going on there, and it is kind of a near end of semester type of lab. So I'm going to shut up in a second. I can even guide you, but any questions at all, and if you're even nervous about it, put in the direct chat. But like anything I can do to try to help you write clearer lab reports on that one, or have an easier time writing them, is with the first priority of today's class. And even this diagram, by the way, like if you're already working on it, this diagram is not about that. I mean, it's related. You can tell it's related, but I could say right now that this diagram would not be a diagram that you would not. This does not belong in your formal report. Okay. So I'm looking in the chat. So right. Okay. So one thing is so somebody in the direct chat is asking me about the component FBDs, the component free body diagrams, and how to solve for them. And that is definitely my focus here. Yes. And I am going to talk. That's exactly what I'm going to talk about. And I could talk, believe me. I mean, that is what I'm going to talk about, is the component free body diagrams and how to solve. But this is an opportunity if you want to specify even further, any of you, if you want to be literally like, I don't know whether to make this minus or plus, or I don't know why this has a cosine or something, like, I can just talk and I will just talk. But sometimes I just talk in my direction and it doesn't address the very obvious thing that somebody needs. So I'm going to pause for a second and but yes, one person put in the direct chat, can I talk about component diagrams and how to solve? And yes, I will totally do that. But if you want to ask me something even more specific, I'm going to give you a moment to think. Okay. And the time's not up. Like, you're not going to lose your opportunity now. If you think of anything while I'm talking, please do, or put in the chat. And I know I sort of did this on Wednesday, but like, let me back up for a second and say, one of the reasons I really like this lab, slow down lab number 5, is to me, it is a surprise, right? I mean, I think that when you write up your report, I'm just thinking what I should write there. When you write up your report, you are ultimately trying to explain why something takes more time to go down an inclined plane than it does to go up the same inclined plane in a natural round trip, right? Maybe I even phrased that badly. Like, if you send something on a natural round trip on a rough inclined plane in the lab, what I think you all find ultimately, or most of you found, if you do it under real but controlled conditions and you do it over and over again, you find that flicking a marble up a rough inclined plane takes less time to go up than it does to come back down. That means on average, it is going faster on the way up than on the way down. Now, first of all, I think that is surprising. I think it's completely real. I think it's true. And I think it's not hypothetical. I think it's experimental. But I think that if at some level that doesn't slightly, or at least it didn't slightly surprise some of you at the beginning, then that may be an issue. Like, I think it needs to be recognized that that's not obvious. So what you're attempting to do in the lab is explain how that surprising result could be true. And the ultimate explanation absolutely has to rely on the solution of component free body diagrams. Absolutely. And ultimately, when we look at the component free body diagrams, what we're really trying to show is the fact that the up diagram differs from the down diagram only in the respect that the direction of friction flips from one to the other. And that ends up making all the difference, right? No magnitudes change, only one direction changes, and that makes all the difference. And so in order to actually do this report right, you do need to understand how friction works. You need to understand how component diagrams work. And I'm going to do it again. Right, I'm going to cut to the chase again right now. I already set this up in a large way last time, but let's talk about on the way up. I want to zoom in and go a little slower with one thing that I said very quickly last time. And again, this is one of those physics things. Sorry, I'm like standing out of the screen. This is one of those physics things where, and it's kind of like preparation, you know, in terms of exams and stuff. Like, I'm honestly trying to tell you that the more you engage in what there is about this that is confusing, the more you will show yourself and me where the clarity is. Like, to actually explain this properly and do this physics properly, I think involves allowing oneself to admit that something is confusing about this and then cleaning up that mess rather than skipping over the mess. So, and I think the part of the specific mess of this, or the specifically intimidating part of the component diagram, is exactly why in the end are we breaking up gravity, and even more specifically, why are we saying that mg sine theta is along the plane and mg cosine theta is against the plane? That's what I want to explain even a little bit more slowly today. And again, I want to say that I mean, I don't collect your lab reports. I know that, but this problem does usually end up on the final exam, or problem based on this. And I want to say that the best explanations of mg sine theta and mg cosine theta and all that are explanations that acknowledge that there is something to be explained. It's not just a memorizing thing. So forgive me so again, I'm welcoming any questions about this. I was very confused. And anyway, but I'm going to do it again a little bit more slowly, and I'm going to contrast it with some other things today. You'll see what I mean. But do stop me at any time. I'm saying, oh wait, sorry. Hold on. Okay. Again, this is just my DFP, my picture of the situation. I've got this block or this marble or whatever that's sliding up a rough inclined plane. Because it was given some initial velocity v naught, right? So that's, I'm just drawing that picture to show the orientation of my slide. But then the pure free body diagram of that situation. Oh, and sorry, there's one other given. And the one other given is that there's a coefficient of kinetic friction mu k. So the pure free body diagram of that is mg down, because mg is always straight down. Then the normal force being exerted perpendicularly to the plane of contact, from the normal force being exerted from the plane onto the sliding object, being exerted in a direction perpendicular to the plane of contact, and then friction opposing the motion of the block or the marble relative to the plane. Okay, that's my pure free body diagram. Like we said Wednesday, like I know this is old news, that's the pure. Okay, but then we have to break things up into components, right? Now, what I want to show you first a little bit more slowly right now, and then I'm going to show you something else. What I want to show you first is how I get the components that I get if I choose an x-axis that is lined up with my direction of acceleration. This is like what I did Wednesday. I'm just going to do a little bit more slowly. And this is what we're recommending that you do in the lab. Like Okay, again, I'm on purpose, I'm repeating something I did Wednesday. I'm just trying to be clear. I'm going to, again, slightly more slowly do what I did Wednesday, but just so you know where this class is going, if people don't ask questions, I'm going to show you again the coordinate system choice that I made Wednesday that you're making in the lab, and that leads to like all the mg sine theta, mg cosine theta stuff. But then what I'm going to do after I do that is show you what happens if you do the other coordinate system. Okay, that's going to be new, that you did not do in lab, and that's like the second half of this class, just so you understand what's happening. So I'm making a contrast in this class of what happens, what are the results, how does F net equals MA work, how do you solve in one coordinate system or versus the other. I'm going to do both, and hopefully that will really answer the one person who's asking in the direct chat about components. You're really going to see components now from both perspectives. But anyway, so the first part is a little bit repetitive. Hopefully it'll clarify for people. The second part is the totally new part. So in this first part, I am doing the general strategy that we recommend in physics, the strategy of choosing an x-axis to line up with the positive acceleration, right? So I'm saying, okay, our choice is that our axes look like this, right? This is the choice. We're like tilting our head. We're tilting the graph paper through which we're looking at the inclined plane. If that's our choice, that means every force vector that does not lie along one of those axes has to be broken up into components, right? Under this choice, then, like we said Wednesday, under this choice, and I'm trying to emphasize, whenever people break things up into components, they have first made a choice of what their axes are. People don't always draw them or make it clear, like in textbooks or on websites. It's not always obvious that that's what's going on, but that is what's going on. You can't break anything up into components until you first decided what the components are supposed to look like, what your axes are. So if we choose to tilt our coordinate system, then it's gravity is the problem. Gravity is like the line that's not parallel or perpendicular to one of these axes. So gravity must be resolved, like we said. Wednesday. So we zoom in on gravity. Zoom in on mg, on the mg vector, right? So, and again, stop me if I turn the page too fast or whatever. So here's the zoom in. Gravity is going straight down, right? But we're saying that is the hypotenuse of its own right triangle. We're saying gravity, the vector, is doing it has some gravity. That vector is really the sum, S-U-M, of two components, an x component and a y component. But x and y now are like on a tilt, right? Like remember, in the background of our, we've got, in the background, we've got, I don't know if, yeah, you can't really see yellow. In the background, we've got this x-axis and we've got that y-axis, and we're trying to break up gravity into those two components. So what we say is, okay, so we're tilting our head so much that we're literally tilting our right triangle, right? And we're saying that the hypotenuse of the right triangle is actually a vertical line. And again, that's new to people, but we're doing it because we're trying to line up our axis with the expected direction of acceleration. So we're saying gravity does some amount that way and some amount that way, right? And notice again, I'm saying like tip to tail is how you add vectors. That this one leg of this triangle plus the other leg of this triangle equals the hypotenuse of this triangle. And we're really, really saying if gravity is pushing down, that means it's pushing to some extent down left and to some extent down right, right? We're saying physically that gravity is doing, in fact, let's say this, like, so this is X, right? And this is Y. So in English, we're saying like here, this is pushing, sorry, pulling along the plane, right? That's one job that gravity is doing. And the other job is doing is pushing, is pulling into the plane or against the plane. Right? Because we've tilted the plane, we're now creating a situation where the weight of the object is accomplishing two things rather than one, right? So one of these is mg sine theta, and one is mg cosine. Oh, sorry. One of these is mg sine, and one is mg cosine. The question is, which is which? Now, I know you've already been told in lab, or you already realized in lab, or I already told you Wednesday, but I really want to say again, like, I think for many of us, it's confused. Like, you might have gotten used to it. You might have memorized which one is which, but honestly, which one is which has everything to do with how I labeled the angle in the original diagram. Like, well, anyway, like, it's not actually a thing that can be memorized. We could easily slightly tweak the situation, like on an exam or whatever, and then you'd have to refigure out the components. So how did I figure out these components? Another way I'm putting it is like in other vector problems, people sort of get used to the idea that cosine goes with x and y goes with sine, but that's actually not always true. And here it's not obvious what x and what, I mean, it's not always true that sine is vertical and cosine is horizontal. What is always true, and you don't want to memorize that. What you want, and breaking up vectors into components is going to be a thing like for the rest of physics, definitely including physics 204. So what you want to memorize, if anything, is that cosine always goes with adjacent and sine always goes with opposite. That's true. But the problem I always had when I'm just, sorry, there's something else in the chat. I'm going to get to it in 1 second. But so what I want to show you now, even though I know I sort of quickly said it last Wednesday, but now I want to show you more slowly, like, how did I decide which one is sine and which one's cosine? Or put another way, how did I decide opposite what, adjacent to what? Like what is the angle in this triangle that I'm looking at opposites and adjacent to? Frankly, when I was a student, I understood SOHCAHTOA, I could do it sort of, but I never actually, I knew that they were always saying sine is, the sine of the angle is the opposite side over the hypotenuse, etc. But I never knew how they came up with which is the angle. There's two angles to choose from besides the right angle. So to me, what was sort of weird was like just that. How did they know which angle they were looking at? And I want to show you, and there is rhyme or reason to this, but okay, hold on. Something in the chat. Let me just pause for a second. Hold on. Oh no. Oh my God. This is exactly the right question that's in the chat. Hold on. No. Okay. All right. So exactly what I'm about to do. What I'm about to do, is exactly what's in the chat. Hold on a second. So I'm going to put in my words and then, no, I'm really glad that, it feels more like teaching. So I'm going to read, I'm not going to say the person's name, but somebody in the chat is saying, this might be a dumb question or a misunderstanding on my part, but they say, is the angle that we use for cosine and sine in that triangle the same as the angle of the ramp, or do we have to solve for it? Because in class, I assumed that it was the same as the angle in the ramp. But when we went over it, it seemed like we had to solve for it. So sorry for the long explanation. That's like exactly the point. I'm so glad someone's admitting to that. Like, that is exactly the issue. Like, what I'm saying is, so thank you. And please submit for points for that or whatever. What I'm saying is that the only angle we know, is the angle of the ramp, the angle that was given right here in the blue. Hold on, I'm just going to change the chat. Change the screen thing. That blue angle is supposedly known. Like in the lab, you like actually probably measured it with rulers or whatever. We know that angle. The angle, let me be even more clear. Hold on. We specifically know what's given is the angle between the ramp and what we regard to be the horizontal, like, right, how elevated the ramp is from a horizontal line, a horizon line, a tabletop in the lab. Some people call this the angle of inclination, how inclined our ramp is. Yeah, sorry. That's okay. Wait. Now that's the thing that's given. That's the only thing we know. So ultimately, when we say sine of theta or cosine of theta, yes, it has to be expressed in terms of that angle, the only one that we actually know in the lab or that we were given. Every bit of math we do has to be expressed in terms of that angle. But the reason the person's asking, the reason it's confusing is like, the question is, where is that angle in this triangle that I just drew? Like, that is exactly the issue. Like, what, like, if, like the side of this triangle that takes sine must be the side that's opposite some angle we know. The only angle we know is the angle of the inclined plane. But that means that somehow we have to find that angle in this triangle. It's in other words, it's either this or it's this, I hope, or if it's neither, we better, we really have issues, but like, we don't know offhand which one. So the thing that we're solving for, the thing that I need to solve for is to show you how you realize which one of these angles in the triangle is the same as that theta that you're given in the lab. And I'm going to do that, right? That's exactly what I want to do right now. And please tell me in the chat if, like, when I'm done, if that's what you're asking. But yeah, like, we know one angle, but it doesn't seem to be obviously either of the, I mean, this is a whole different, it looks like a different triangle. So, okay, you get my point. Okay, so what do I do? It's ultimately, this whole thing is a question of, can we express the unknowns in terms of the knowns, or express the unknowns as functions of the given constants? How can we find theta in our rotated MG right triangle? Well, one way is to do raw geometry. Like here, I'm just going to zoom in again. Here's the MG hypotenuse, right? That's MG. This is one side. This is the other side. But now look, if I like interpose, no, that's supposed to be a different color. If I interpose a horizontal right in the middle of that triangle, right, and go like this, then this right here, and stop me, please, or tell me, oh, there's something else in the chat. I'm going to look in the chat in 1 second. But I'm saying, if I interpose a horizontal into this triangle, then that angle between the horizontal and that dotted line is theta, right? So if that's theta, then this must be 90 degrees minus theta, right? Like, I have, like, the top half, like this whole big thing is one big right triangle, but it's made of two small right triangles, right? Because the horizontal is definitely, by definition, oh, I keep standing up, sorry. The horizontal is definitely by definition perpendicular to the vertical. So if that angle there to the left but is theta, then the angle up to the top right must be 90 minus theta, because that, I don't know how else to say it, but that, right? But then if that top thing is 90 minus theta, and this is a right angle, then if the top is 90 minus theta, then the bottom must be theta. And please stop. I'm going to, right? So I think what I've just, now there's other ways I want to say about, other things I want to say about this. But first of all, I am right now arguing that if I think about it geometrically, and I wish I had other colors, don't I have other colors? No, I do. Like, I think that I've just shown that this right here must be theta. It, like, this angle here must be the same as the original theta that you measured in the lab. And that's my first, and I will stop and look in the chat, but if that's theta, then this is the opposite side, and this is the adjacent side. And that's important. Like, I don't think that's obvious. I think it's true and important, but like, it's not, but then once you see it, and by the way, and I'm going to stop and look in the chat. One reason I'm going through this is if you're really understanding the question that the person asked in the direct chat, like, you'll see that we have to go through all this because you can't just at the end memorize, okay, one is mg sine theta, the other is mg cosine theta. Because like, we clearly could do this whole experiment where the original given angle was at the top of the inclined plane, not the bottom. And then all the results would flip, not the ultimate answers, but the sine and cosines would flip, right? So it totally depends on what you originally view as your given angle. So far what I'm saying is that I'm going to just, I see there's something in the chat. Let me just pause for a second and see. Oh, right. Sorry. So someone's asking in chat, would this be a case of alternate interior angles? Would this be a case? I do love alternate interior angles. It's good. Two parallel lines are cut by a transfer. Do I see the two parallel lines are cut? The truth is, somewhere in there that is going on. I don't actually think that literally the two angles, I love that concept. I mean, when I think of just a quick sidebar, no, I love, and if you can see the alternate interior angles and if that's working for you, then by all, I mean, if you see the geometry any way that you see it and it works, by all means, go with that. To me, alternate interior angles are when you have two parallel lines cut by a transversal like this. I think what I always think of the alternate interior angles as the inner corners of the Z that's formed. Like, I think this is an alternate interior angle with that, and that those are congruent. This is like that. I don't think it's exact. It's certainly the same principle or same, but I don't think these are exactly alternate interior angles. But like I think that's when you have a Z and it's like the inner corners of the Z. But okay, cool. Okay, but so the first thing I'm saying is if you buy this reasoning, then okay. So I'll say it one last time. I'm saying that side that goes along the plane, is opposite to an angle. What angle? The angle that's the same as the one that we originally measured in the lab. That's the point. Like, obviously, I could look at this other angle in this triangle. I could look at the top angle, the one that's 90 degrees minus theta, and then, and then I could express, then what was the adjacent side becomes the opposite, and what becomes the opposite becomes the adjacent. It would all, but I don't want to look at that angle because I want to express everything in terms of the original theta. So I'm finding the original theta in this triangle. That's what I'm solving for, right? So then I say, thus, right. Thus, I move. You see, how can I put this? Well, no, okay, I'll do that. I won't do that in one step. I'm saying thus we have so we zoomed in on gravity in order to get these two components. But then the whole thing of vectors, right? I zoomed in on gravity to get these two components. I'm saying that mg sine plus mg cosine equals mg. That's literally what I'm saying. So I'm saying the sum of those two is equivalent to the original. But now the power of vectors, and it really is subtle, is that I can move vectors anywhere I want and they still mean the same thing. Like, a vector is an arrow. Its length means something. Its orientation means something. But where it is on the page doesn't mean anything. Therefore, I can bring it anywhere I want on the page and it still is itself. So I can now substitute mg sine and mg cosine in the original diagram, right? Now I can say, I can take out the mg that's not along an axis and put in these components. So in my component free body diagram, I can say, okay, the normal force is going like that, and gravity is going like I just moved the mg cosine theta from the tip of the mg sine theta to its tail, because now I'm not expressing addition anymore. Now I'm literally drawing all the forces that are acting on an object. And there's also friction there, and friction the whole time has been going like, sorry, no, if we're on our way up, sorry, we're on our way up. So then friction's also going down. And that's our component free body diagram for the up trip. But let me now add, so partly what I just tried to, I tried to just use, oh wait, someone else is in the chat. I keep skipping. Right. No. This is great. Like, that's what I'm trying to, so someone else in the chat said that makes a lot more sense. Thank you for clarifying. I tend to assume that the other angle would have been the theta because it's the one connected to the other forces. Right. The other angle really looks like it is theta. Exactly. That's why I'm going through this. I don't think this is obvious at all. But yes, I do think it makes sense once you see it. But right, no, good. I'm glad you're saying that. And here's the thing too. Let's physically consider what we're saying here. Okay, like I just did geometry, but let's stand back. This is physics. Let's try to make sense of this. What we are saying, and I'm going to flip the page. Tell me if that's bad, if you want to flip back. We're saying okay, I'm going to pause for a second. Now, this may be what I'm to really understand this mg sine theta thing. Like, let's step back, and I'm saying mg sine theta is the component of mg that is responsible for pulling the ball or whatever, the object, along the plane, like along. Like, we could say that mg sine theta is pulling the ball down the plane. We could say that mg sine theta is pulling the ball down the plane. But the whole point of this whole diagram is that's ambiguous to say that. Like, mg cosine theta is also pulling the ball down the plane. What we're saying when we make this diagram is that there's now two different ideas of down. Gravity by pulling straight down. Once you tilt your table, down takes on two distinct meanings. There's down along and there's down into, right? And the sum of them together makes the entire job of downness, of weight. So some portion of the object's weight is responsible for keeping it against the plane, balancing the normal force. And the other component of the object's weight is responsible for sending it along the plane. And now what we're arguing is that component, that fraction, right? Because sines and cosines are always numbers less than 1. You could think of them as fractions or percentages even. Some percentage of the ball's weight is responsible for sending it along the plane. And what we just determined is, assuming we're measuring our angle a certain way, we just determined that the percentage of weight that's responsible for accelerating it along the plane is the sine theta component, right? So imagine for a minute, just to take this, to analyze it, to bring it into relief. Imagine there's no friction. Imagine mu sub k is equal to 0. Then the net force along that component, I mean, I'm sort of skipping steps here, but the net force would be mg sine theta would equal ma in that direction, in the what we're now calling the x direction. So the m, we could divide both sides by m, and a along that direction would equal g sine theta. Wait, so let me put on there. Like if there's no friction, right? G, according to what we're saying here, we're saying if there's no friction, the object will accelerate along the plane, not at a rate of g, but at a rate of g sine theta, i.e. some fraction of g. Right? Like g sine theta is some fraction of g. The whole thing about sine is that sine, the sine of angle 0 is 0. And as the angle gets bigger and bigger, sine gets bigger and bigger. The fraction of free fall that occurs on a slide gets bigger and bigger as the slide gets more and more elevated. Doesn't that make perfect sense? Like, I'm not saying it's obvious, but once you think about it, doesn't it make sense? What we're saying is like, if theta equals 0, then A equals G times 0, i.e. nothing. If the plane is flat, the object won't accelerate at all along the plane. But if like theta is like 30 degrees, then A equals G times the sine of 30, which is to say G times 1/2. Like 4.9 meters per second squared or whatever, right? And then if G is 45 degrees, then the acceleration will not be half, but will be like 71% of gravity. And then if theta goes to 60 degrees, sine of 60 degrees is like radical 3/2, which is like 1.7 divided by 2, which is like 0.866, right? So what I mean, okay, let's quick chart, like, sorry. Like, do you see what I'm saying? I'm just doing the signs of like angles that we all know, and I'm converting them to decimals. I'm rounding, right? So basically, as the angle gets bigger and bigger, the percentage of free fall that we're getting is bigger and bigger. The plane dilutes free fall effect of gravity, and that's why Galileo used them. The plane slows down gravity, makes it easier to study, the less steep the slide is. But the reason sine is the perfect expression of this is that cosine goes backwards. Cosine goes the other way. Okay. Oh, back up. Yes, I can totally back up the page. Yes. Is that the page? Okay. Yes. No, I'm glad people are getting. Yes. And tell me if this is the correct page or if you want me to. And I think that chart sort of says everything. Oh, okay, cool. Okay. So what I'm trying to say to everybody is actually at the end of the day, Like we did geometry to figure out which one's sine and which one's cosine, but it actually makes so much sense which one is sine that we actually could have figured it out without even doing geometry. We could have just asked ourselves which of the two components, right here. In order to figure out components, you can do geometry or you can cut straight to the chase and always use this test. You could say the component which takes sine of the angle. I mean, one component is always hypotenuse times sine, and the other is always hypotenuse times cosine. So the whole issue for all physics students and all physics, the issue, if you're up to that issue where you get what's going on, but you don't know whether to pick sine or cosine, you're in the right place. And that's what I'm explaining right now. Like, you're not alone. But in order to know which one takes sine and cosine, don't think sine is always vertical and cosine is always horizontal. That's part of the lesson that I'm saying here. It's not that simple, but it is as simple as this. Sine of 0 is always 0, and sine gets bigger and bigger as the angle gets bigger. That's what sine super. Cosine counterintuitive. Sine super, cosine counterintuitive. The cosine of 0 is 1, and as the angle gets bigger and bigger, the cosine gets smaller, right? So it wouldn't make any sense for the component along the plane to take cosine, because as the plane gets steeper, we want the acceleration to get bigger. Right? So the component which takes sine theta is always the component which must physically disappear, which must disappear, which must not be there when theta equals 0. You see what I'm like? When theta is 0, mathematically, the sine of 0 is 0. Physically, in this case of the inclined plane, when theta is 0, gravity is not sending, all of what gravity is doing is balancing the normal force. Gravity is not sending you along anything anymore. So the sine component is the component along the plane, because that's the one that disappears when the plane is flat. I mean, you may have to think about that. Again, I'm not saying that this is obvious, but I am saying it makes sense. And there's like no other way to think about it once you think about it that way. The cosine, on the other hand, and now I'm going to move on in a minute, but well, actually, let's move on. So, well, okay, I'm looking in the chat. Good. Or maybe actually, okay, there's things in chat. Well, okay, wait. So to be honest, no, I totally appreciate Katie's question in the everyone chat. That's awesome. It's a great question. But actually, what I'm actually trying to say here is actually the answer is no to that very fair question. It's not a fair assumption that sine is always the x-axis. In fact, like often that sine isn't the x-axis. What is a fair assumption is one of two things. Either one, what is fair is that sine is always opposite the angle. But the issue is usually like, what's the angle? So the really fair assumption to make that I'm saying is that sine will always be along the axis that will not have a component in the theta 0 case. Like you do have to think about that, but that's what I'm just being honest. It's a great question, but no, don't assume that. Don't assume what you're saying. I mean, don't assume that sine will always equal the x-axis, but do assume that sine will always be on the axis that won't be there at all when angle is 0. What do I mean the axis won't be there at all? I mean, when theta is 0 here, mg, it does not anymore do any job of pulling the thing. Like we're saying here, the two components are pulling along the plane and pulling into the plane. If theta were 0, mg is only pulling into the plane. There's no pulling along the plane anymore. So that must be the sine. I don't know if that, oh, got it. Okay, cool. Great. Okay. So, but great question. So now I'm going to go back. So this is my argument for how to resolve sine and cosine, which I do think is tricky here. And you don't want to memorize, like if we were to take an exam and we were to give you the angle in the original inclined plane, if we were to give you the angle up here rather than down there, then everything you do is like all the sines and cosines are flipped with each other. So you don't want to remember. Okay, you got my point. So it's 155. All right. So now, back to the FBD. Oh, well, I guess I did this already, but yeah. So then the FBD looks like this, we said. And it doesn't matter if I drew friction above or below mg sine theta, they're both coming out the same thing. Notice the mg cosine theta. Note it's the mg cosine. Oh, well, okay. Actually, now let me get back to the original person's question direct out who asked about components. So what would we do now? How do we then solve? They asked originally, like, here's a free body diagram. This is just for the up trip. It'd be different for the down trip. But how do we solve? Well, now to solve, we apply F net equals MA, one axis at a time. And now we can, because everything that's happening is along axes, one axis at a time, right? Like now we can go to the y-axis. We can go to the y-axis first and say, okay, n up the y-axis minus mg cosine theta down equals MA along the y-axis, right? And the whole reason, the whole benefit of this strategy, like everything I'm doing is necessarily what I have to do, given the choice I made of lining up my axes in a certain way. Now, that was a choice. This is all based on that choice. But here's why that was a good choice or a smart choice, is in this coordinate system, the acceleration is entirely horizontal. We chose an x-axis to line up with A. So A is fully along X, in other words, A sub Y is 0 in this coordinate system. The object is neither flying off the plane or into the plane, right? So in this coordinate system, we have the advantage of saying that mg cosine theta is fully supporting the normal force, or the other way around. And by the way, that makes sense to me, because when theta is 0, cosine of 0 is 1. When theta is 0, the normal force up fully equals the mg down, right? And as the plane gets bigger, as the angle of inclination gets bigger and bigger, as theta gets bigger and bigger, cosine gets smaller and smaller, right? So when you get all the way up to fully vertical, the cosine of 90 degrees is 0. Note, cosine of 0 equals 1. Cosine of 90 degrees equals 0. So the normal force gets smaller and smaller as theta gets bigger, right? Doesn't that make sense? Like the plane supports less and less of the plane as the plane gets steeper. And what did I just say? The plane supports less and less of the block as the plane angle gets steeper, to the point where it's fully vertical, doesn't support the block at all. And the block fully is in free fall, right? You could also even argue well, as we'll see in a minute, if the normal force dictates friction, what we're saying here is as the angle gets steeper and steeper, the frictional effect gets lesser and lesser. Cosine goes down, sine goes up. It really makes sense when you really think about it, that sine is the along and cosine is the against piece of gravity. But okay, but all we learned there from the y-axis is that the normal equals mg cosine theta. Who cares? Because now we can go to the x-axis. And in the x-axis, we have mg sine theta plus friction equals ma in the x-axis. And that's all of the A, right? And we know, we did this yesterday, Wednesday, but we know that friction equals mu times the normal. So we have mg sine theta plus mu times the normal, equals ma. But from the y-axis, and this is why we did it all this way, from y-axis, N equals mg cosine theta. So we can sub in. So we say mg sine theta plus mu mg cos theta equals ma. And we can factor out an m from both sides, divide both sides by m, and we have the a of the plane going up. Now, what, right? And what I said yesterday, well, I'll just finish this. Then we compare to down. So we have up, a equals g sine theta plus mu g cosine theta, whereas down, a equals g sine theta minus mu g cosine theta. And what we said yesterday, this makes all the difference. I'm saying this quickly because I think I said this Wednesday, but again, if there's, this is the punchline of the lab. So if there's questions here, you should ask here. Otherwise, there's something else I'm about to do. But once we did those components that way, we could get that the acceleration, the whenever I say up or down, I mean while the ball is going up or going down. The acceleration itself is always pointing down. Like the acceleration is always pointing down. But while the ball is going up, it's this huge number, g sine theta plus mu g cosine theta. And while the ball is going down, it's this smaller number, g sine theta minus mu. Like I'm assuming in this whole coordinate system that down is positive and up is negative, for what it's worth. And you could do it the other way, but then you have a lot more negative signs. So the acceleration is bigger when you're on your way up. Therefore, the average velocity, you could show with the equations, you could plug in the numbers and you'll see that the average velocity is greater on the way up. And therefore, the time is lesser on the way up. You go up faster than you come down. Again, in English, and again, if I were your lab, I mean, I'm not grading them, but I would be looking for this kind of analysis. And I'd be looking for, in the end of the day, do you break down into words, say on the way up, the ball loses speed faster than it gains speed on the way down. That's literally what we're saying. I mean, and that's like a mouthful. Like that is not I don't know. I don't think that's easy. I just think it's true and interesting. And I think it's interesting because it's surprising. Okay, but now, so I'm going to pause for a second if there's any questions on that. But I know I have 16 minutes. I'm not going to read you the whole thing, but I'm going to show you something in 16 minutes that you are responsible for. I'm going to pause. All right. Oh, is that a hand or is that me? Is that a hand or is that me? Wait a minute. I can't. Hold on. If there's a hand, definitely if there's a question, ask it, please. No, you're good. We're good. Okay. Then here's what I'm going to do. In order to really, so I think we broke up gravity because actually, like it's hard to break up gravity, but once you do, we only did a couple of lines and we can see, we can solve F net equals ma fairly quickly if we break up gravity. What I'm going to show you now is what happens if you don't break up gravity. What I'm about to show you is just as correct. And it seems like it would be easier, but I want to show you why it's actually harder, why we do the thing that we do. Like, so now, and I'm not even going to worry about friction here. Could we have done this if the whole issue, and I maintain the whole issue of this, the issue that either confuses people or that people blindly memorize at their own peril, the whole issue is that we broke up gravity, and that's like a surprising thing to do when we got mg sine and mg cosine. So the question is, could we have analyzed this without breaking up mg, i.e., could we not? Could we have stuck? Could we have maintained a customary XY coordinate system? Like, why didn't we just keep our head untilted and just be like horizontal, vertical? Could we have done that? And the answer is yes, we absolutely could have. This is the power of physics. We could have, and I'm going to do it right now. And I'm going to do it somewhat quickly. But what I'm hoping to show you here is that it will work. It'll get you the same physical results, but it's actually harder. But you are responsible for it. Okay. So here's a pure free body diagram again, right? It looks like this: mg down, normal, and I'm doing without friction this time to keep things, so normal up, and that's it, right? We have, right, pure FVD. So now what I'm going to do is I'm going to stick to, let's choose horizontal, vertical as,
Wait, shouldn't there be friction on this?
well, except I'm saying we're now going to set aside friction. We're saying let's assume.
Oh, I
just-
missed that.
sorry. And we could do friction. It's just going to make it even more like yeah. So right now, just to be clean, I just want to focus on what happens with the. But yeah, good question. Good. All right. So, so what I'm trying to do now is do the thing that I think we all would have done if physics didn't suddenly get weird on it. Like what I think most of us would have done is say, okay, let's choose let's stick with our everyday customary horizontal, vertical coordinate system that looks more like this. Like, let's just say this is Y and this is X. In fact, since we know the thing is going to slide down, I'm even going to make one more correction. Let's try to be a little bit clever. Let's say, sure, that this is Y and that's X, but let's call down positive Y just so we can avoid some negative signs. So that'll be, and left, in other words, the direction the thing is going will be positive. So, but what if we do that? In other words, what I'm going to do now for 11 minutes, not 12 minutes, is show what would happen if instead of breaking up gravity, we broke up friction, we broke up the normal force. And indeed, if we do this, we would also have to break up friction, which would make it even harder, but I think this will be hard enough. So if we do this, then we have to, then we zoom in, right? Zoom in on the normal force instead of, right? And here's the normal force. It looks like that. So we're zooming in on it. So it has two components. Like this is a normal force, right? Two components. And this is a right triangle. Now, one of these two angles is theta. This is exactly like the other person's question earlier. Like, I'm going to divide this into, let me make this even bigger, but I'm zooming in on the normal force. I'm choosing its two components. And I'm trying to resolve into those two components. So here's normal. It's made of two components, a horizontal. I always draw horizontal first, tip to, and from its tip, I draw the tail. Oh, sorry, I didn't mean to do that. I did not mean to do that. So I've got normal. Now, one of these is normal times sine theta, and the other is normal times cosine. I don't know which is which. I know this is a right angle, but here we go. If I do geometry, I don't think this angle at the bottom, is not the actual original given theta. It's not. Like this is 90 minus theta. How do I know? Because remember I'll put it right here. Because the plane goes like this, right? This is theta. So in other words, if I'm drawing this and I'm looking at this, okay, this is alternate interior angles for real, for what it's worth. Like we're looking at this angle here is literally no, this is it's not alternate. Like the alternate interior angles would be congruent, but we're looking at the angle right above the alternate interior angle. We're looking at its complement. I don't know how to say this better, and you can put it in the chat, but if the original angle theta was between a northeast line and the horizontal, we're now looking at a northwest line. It's not the same angle, it's the complement of that angle. Think it through how you want, but this angle down here is not theta. This angle here is theta. So what I'm claiming is that this X gets the sine, and because it's opposite of theta, and this one gets the cosine. And if you don't like that, because that is a little surprising, this is part of why I'm doing it, realize that if the angle went to theta, if the angle went to 0, n sine would disappear, which I think makes sense. If the plane were flat, then the normal force would not be pushing to the left at all. It would be pushing entirely up if the plane were flat, right? The only reason that the plane is pushing to the left at all is because it's inclined at some angle. And the bigger that angle gets, the more it's going to push to the left. So that leftward component of the normal gets the sine. Think about that on your own. It's not obvious or easy, but it is correct. And it does make sense once you let it sink in. So I'm saying the free body diagram that we get, the component free body diagram then, without friction, just because I think it's hard enough without friction, then looks like this: mg down, n sine to the left, and cosine to the top. I'm looking at the time. Okay, we got 8 minutes, right? This is, again, without friction, because it's hard enough. And something you couldn't deal with friction. Like, once I'm done with this, you could put friction in, and it's just, I'm just trying to go piece by piece. So this is a component without friction. Now, if we want to know the rate at which an object accelerates along a plane from this coordinate system, we go one axis at a time, right? And we solve. So let's first do the y-axis. In the y-axis, we would say F net, F net in the y equals ma in the y. Now, we said down is positive because that's the direction the thing is going in. So down, we would say mg minus n cosine theta equals ma in the y direction. Does this thing have acceleration in the y direction? Yes, it does, because y means straight up and down. This thing is falling to some extent down, right? We can't cross it out as 0 anymore because we made this choice. So in other words, we'd have to say mg minus n cosine theta equals ma sine theta, right? I mean, the thing is accelerating along an axis. It's accelerating like this. So, So the acceleration has 2 components in this system, and that is actually the angle theta. I'm doing this quickly now, but if you look back, that angle is the angle theta. That's truly alternate interior angles. That is the same angle as was originally given, because that is a true alternate interior angle for what it's worth. So this is a cosine, and this is a sine. And if you're like, wait, what? We're dividing A into sine and cosine now? Yes, now we are, because we didn't choose an axis that lines up with A. I'm trying to, if I'm losing you right now, and I know or if you're just like, there's only 6 minutes left, this isn't even worth paying attention to. Let me tell you right now, if right now you're starting to fuzz out because you're like, MA sine theta, are you kidding me, Abraham? I am going to go on, but honestly, that's my point right there. This is starting to become like weirdly complicated because we didn't do it's correct. It's correct, but it's annoyingly complicated. The whole power of physics is what choices we make at the beginning of a problem. And the choice that we make to set up the problem comes from this whole Galileo idea that the laws are going to work out in whatever coordinate system you're in, but some are more convenient than others. So I'm finishing this. I'm just trying to show you, yes, if you think this is weird, I agree with you. It seemed weird to break up gravity, but it's actually a lot less weird than doing this. Or if you don't think this is weird, I'm going to keep going. So that's my statement for the y-axis. Now I go to the x-axis. I'll just copy it down. Right. So the y-axis said mg minus n cosine theta equals ma sine theta. Now in the x-axis, we look at our picture, we just have n. Like, nothing's balancing n sine theta. No one said anything has to. That's why the thing is accelerating. N sine theta equals ma cosine theta. Okay? Now, what the heck do we do? And this is all again without friction. What do we do now? We have two equations, two unknowns. Like what we're looking for is A. We don't know that, but we also don't know N. Luckily, we have two equations. So what I'm going to do is quickly rewrite each one. I'm going to rewrite each one in terms of N, because that's really what we've always been doing all along, solve for N, and then plug in. So we're going to rewrite each one in terms of N, and then set equal to each other. So the N's go away, and we're left with A, okay? So first we'll do this one. N equals MA cosine theta over sine theta, right? That's one expression for N. Or looking at the other one, if we go to the other equation where we said mg minus n cosine theta equals MA sine theta, if we isolate, we could say n cosine theta equals mg minus MA sine theta. Therefore, divide both sides by cosine theta. N equals mg minus MA sine theta all over cosine theta. So now set the two equal to each other. Mg minus MA sine theta all over cosine theta equals MA cosine theta over sine theta. Oops, sorry. Looking complicated, right? Right. Exactly my point. I mean, are you responsible for this? Yes. But if nothing else, again, my lesson here is this is why we do the other thing. If you think but if you see this whole picture, you're really seeing something. We're trying to learn about forces and Galileo here at the same time. So I could divide both sides by M. They go away. So now I'm looking for, what are we looking for? We're looking to solve for A. So, looking at the time. Actually, wait, today's Monday. Okay, you haven't had new homework for a while. I'm just going to slow down and pause for a second. We're almost there. All you have to do, but I am going to ask you on a sheet of paper to hand in for points. I don't know how many points yet, but I just want you to finish this. Okay, if you're still with me, I'll open up a portal. I want this is just algebra at this point, but I want you for homework, solve for A. I'm saying this slowly because we still have one more minute. That all you have to do is algebra, like collect all the A terms together, divide both sides by whatever garbage there is, like get A by itself, solve for A just by doing algebra at this point on what we have left. But if you've been following, and it'll be like 3 lines. Okay, if you just sit down to do this, it'll be like 3 lines, it'll be like 12 minutes, and you'll get points. But if you've been following me at all, you'll know what the answer is that you should be trying to get. I'm not going to write it here, but I'm just going to say it right now for anybody still paying attention. If you do this right, you should get that A equals G times sine of theta, because that's what we showed earlier in the class. Like if we really believe Galileo, it doesn't matter which coordinate system we use, we should get the same answer either way. But if you spend the 12 minutes tonight to try to solve for A, and get that it equals G sine theta, you will hopefully see 2 things. Physics works either way, but physics works a lot easier one way than the other. And that's why, if you see this, and it's 1:30 now, the strategy always from now on in physics is to line up and is to choose an x-axis so that it lines up with the direction of acceleration so that you don't have to divide A into cosine and sine, so that you don't have all of this. As hard as the other things seemed, this is a lot more algebra. And hopefully you'll see that if you spend 12 minutes to finish the algebra and get A. So, and if you don't do it, you don't do it. But I'll open up for, but you've been very patient. Hopefully that was clarifying, or it will be when you do it tonight. Have a lovely evening. I'm totally not leaving. I'm answering any questions you want, but I am stopping the recording. And I'm thanking you. Yes, have a good one. Exactly. Great questions, people. Seriously. Just okay. And I'm stopping the Yes. Oh, wait, we do have class Wednesday though, don't we? Wait, yeah, we do. Right? Yeah, we always do it, John Jay. For good or for bad. Yeah, Katie's looking at me crazy, but I mean, and look, if you can't come, you can't. No, I think we do.
I don't think we do.
Yeah, I don't think we do. I think
Wait,
we have off.
Yeah, I don't think we have
Wednesday?
class.
Yeah, Wednesday we have off.
I don't have my other classes.
Wait, really? Oh, wait, if that's true, certainly it won't make, if that's true, like, that's awesome. I mean, don't get me wrong. I'd like to have a holiday, but that's never happened before. Oh my God. Okay. Well, still try to do, then well, hopefully okay. Well, I'm glad you're really.
Yeah, I'm like, I thought it was really weird on my calendar I was putting it in, but
No,
I
you
was just
are.
like, I guess there's no class on Wednesday.
Okay, no, if there isn't, there isn't. I'm not holding it if there isn't. No, don't get me, there always have, wait, I gotta stop the recording. Oh my God.